Hey everyone, it's Dr. Calkins. Today we're going to do week 11, chapter 15 homework questions that were submitted on discussion forums. Looks like students started off not liking the math, so let's go through some of those. Notice both of these questions are the same, 2 and 3, and then 4 and 5. They're asking the same thing just with a different idea. Remember, our help for pH kinds of calculations like these comes from our table. So you have one of these in the front and the back of your lab book. So remember, this is our most useful tool for this. In this particular problem, they say pH of 4.72, and then they want the hydrogen ion concentration. Hydrogen ion concentration is H3O+. So we're looking for that. Let's go to our chart. If we have pH and we want H3O+, we need to go down. So 10 to the negative pH should give us that answer directly in one step. So you take 10 to the negative 4.72 as an exponent, and you hit equals in your calculator. So that's second log negative 4.72, and when you do that, you'll get 1.9 times 10 to the negative 5. We can probably guess which answer is going to be hydroxide, because these two answers need to be of that negative 15, negative 14 when rounded up exponent. So you can probably guess it's going to be this answer, because there's the negative 5, there's the negative 10, because they are related through Kw. But again, for this one, a little bit different. You have pH, they want hydroxide concentration. So hydroxide concentration is OH negative, so let's find that on the chart. pH is here, hydroxide ion concentration is there. So it'd be easiest to subtract 14 first, get the POH, and then do exactly what we just did, drop down 10 to the negative POH. So let's do that. So we get 14 subtract 4.72. So when you do that, you'll get 9.28. And that's the POH. So now we can take 10 to the negative 9.28 and get our answer, which again is 5.3. So that's second log negative 9.28 in your calculator. Number 4 is the reverse. They say, what is the pH if you have the hydrogen ion concentration? So remember, hydrogen ion concentration, pH, this is H3O+, because hydrogen ions are attacked by water to make hydronium. So here we need to take our chart and go from hydronium ions to pH. So hydronium to pH, that's going to be negative log number going up. So negative log the number they give us, which is negative button, log button, 6.83, and then it would be second x to the 1 to give you times 10 to the power of, and then we're going to say negative 3. When you do that, you'll get 2.166. For the same thing, they say, what is POH? Well, we know that they are related through 14, so the easiest way is to take this answer down and take 14, subtract 2.166, because remember, pH and POH are directly related through 14, and that should give us our answer of 11.834. So remember, you couldn't have an answer like that that's higher than the pH scale itself, so some of these you can get rid of almost immediately. That's how you do the math problems. A lot of practice in supplemental 12, as well as it's just basic chemistry lab that you should be doing as well. Number 6 says strong acid. Remember, strong means 100% dissociated, so 100% separated. So when you do that, look for the beakers. Here you have H pluses and so that's 100% there. That's the answer. Here we have a couple HAs. Here we have a couple HAs. So that tells us that we're partially dissociated. So those are weak. And this one is completely together. So that's a non-electrolyte altogether. So when you're partially together, partially separated, those are weak. When you're 100% separated, you're strong. And we see that with beaker A for number 6. Number 9 says, why is HF? HF is small in size. Considered weak? Well, weak and small go hand in hand. HCl and HBr are larger because chlorine is much larger with 17 protons, 17 electrons, in this case 18 if it's going to be sharing with hydrogen. Bromine with 35, so much, much bigger than fluorine with only 9. So when you think about this answer, just think about size to some degree or another. If it's small, it's going to stick with hydrogen most of the time. If it's sticking with hydrogen most of the time, it's going to partially dissociate. And it's also going to have a weak conjugate base, so take away H+. So both of those together make B and C correct. The problem with A is HF dissolves in water just fine. It's got hydrogen bonding, so does water. So A is also true, but that's not why it's weak. Being able to dissolve in water is irrelevant. What you do in water, whether you separate into lots of ions strong or very few ions weak, HF tends to be weak because it doesn't separate very much at all. A little bit of acid-base recognition here. So here they say triprotic, we only saw one of those. Triprotic means 3, protic means H+. So phosphoric is from the T4 ion H3PO4, and that'll very quickly find your answer. Just for practice though, hypochlorous is going to lose 2 oxygens, HClO. Sulfuric, H2SO4, that's diprotic. Here was monoprotic, it's got 1 hydrogen versus 2. Hydrobromic is HBr, came from bromide. So again, here we have 1, here we have 2, here we have 1. So these are monoprotic. Here's diprotic, and then here's triprotic, having the 3 H+ ions on phosphate. Number 15 says, who produces more than 1 H3O+ ion? So if you produce more than 1, you're either going to be di or triprotic. We saw this one above, HClO, that's monoprotic, that's 1. H3O+, hydrobromic, that's 1. H3O+. Acetic acid is tricky. It's going to answer number 16 below us. We have some hydrocarbons that aren't acidic, but then we have this carboxylic acid that is. So it's also monoprotic, but it looks tetraprotic almost in the sense of number of hydrogens, but these are nonpolar saturated hydrocarbons that don't count. Carbonic acid, the answer here, H2CO3 comes from the T4 ion carbonate. That -2 gives it 2, and that's going to give it more than 1. It's going to give it 2 H3O+ ions per molecule. 16 says, which one is only 1, but it looks like it has more, and that was acetic acid. Acetic acid is now letter B down here. Hypochlorous still only 1 H. Sulfurous is dropping oxygen, so H2SO3. And hydrobromic back to HBr. So it is important to know your acids. Definitely know how many hydrogens they have, but that's predicted by their charges, and most of these have charges predictable from the periodic table, either by coincidence or by family. So again, because we have those 3 saturated hydrocarbon hydrogens, it looks like we have more non-ionizable hydrogens, because we do. We got 3 of them. But the one that matters, the monoprotic of acetic acid, is the CH3COOH carboxylic acid group. That's the acid hydrogen that makes H3O+ and only once. 17 says hydroxides. So hydroxide is based on group. If you have 2 hydroxides, you're going to be in group 2. Group 2 says alkaline earth metals. So ammonia is going to make ammonium hydroxide, so that's only 1. Aluminum is going to have 3 because it's in family 3. Potassium only 1 because it's in group 1. But the answer, calcium hydroxide, is calcium with 2 hydroxides because it's a +2 metal, like everybody in group 2. Number 25 is more of a trivia question. If you have a pH of 3.2, you're probably dead. And if you're 5.8, you're probably in a coma and almost dead. So really it's very close to what you are normally, which is about 7.2, 7.3 is normal. So 7.0 is not terrible, but it's still a little on the low side of normal. To be diabetic, you're going to be just a little bit lower than that. So it's more trivia than anything else. But definitely get rid of the ones that are super low. That would be super dangerous, if not deadly. Number 26 talks about a full drop in the pH scale. Remember, the pH scale is based on powers of 10. So this idea that it could be 2 times anything is out of the question because pH is based on powers of 10. We take the negative, we take the log to get rid of that power of 10 and its negative exponent. So it's either going to be reduced or increased by powers of 10. So a full unit just means 1 unit. So if it were 2 units, it'd be 100 times, 3 units, 1,000 times, and so forth in that power of 10 idea. So if we're dropping a full unit, that'd be like saying we're going from 7 to 6. 7 is neutral, 6 is acidic, so we're going to be increasing our acidity as we drop units in the pH scale. So increase acidity 10 times as we drop, say, from 7 to 6. So as we go along to 28, we talk about the ionized species in water from ammonia. So ammonia is NH3 and water is HOH. So when ammonia finds H, we get hydroxide left over. So here's your ammonium, here's your hydroxide. So water has oxygen, and notice this is the only one that has oxygen whatsoever. So it can't be this one, there's no oxygen, there's no oxygen, there's no oxygen, so it has to be that one. And this is why. Ammonia is a Bronsted-Lowry base. It's a proton acceptor. Water can be an acid or a base. We'll see that later as well. Number 29 says, which of the following is a strong acid? To be a strong acid, you have to be 100% dissociated. Things that do that are typically big. So HCl, that's a big atom. Acetic acid, if this were strong, it would eat through your lettuce on your sandwich, and it doesn't. Carbon-based acids are weak. Phosphoric acid is big, but it's triprotocan. It's the only one that was weak. And HF is small, and that makes it weak. So this is the only one that would typically make students want to bite because phosphate is huge, and we said big is usually strong. That's the case except for phosphoric acid. There's the one exception. HCl, this is the one that eats cement off of bricks. This is definitely the strong one. Which one is weak? Well, sulfuric acid is battery acid. That's super strong. Hydrochloric acid eats through cement. Super strong. Carbonic acid is what is in rain and in your soda. If it was strong, it would eat through this aluminum can, and it doesn't. Nitric acid is probably the strongest of the bunch. It dissolves lots of metals, just like in the movies. So this is the one that dissolves in your bloodstream, dissolves in soda when they put carbon dioxide into water. Carbonic acid. Not sure that one was asked, but it was a good practice. So 31 says, which of the following is a weak base? To be weak, the easiest way to know weak is to think about solubility. Things that are in group 1 and group 2 from our solubility table in our previous chapter would have said group 1. Those are strong. So the only one that's left over is the weak. So because all of these are in group 1 metals, those are the ones that were soluble along with calcium and barium in group 2. Everybody else would have made a precipitator in some cases, except for these group 1 and 2 metals. So ammonium here, that's the unique one from this chapter, not from the last chapter. As we go to strong base, use that same logic. Do we have anybody from group 1 or group 2? In particular here we have potassium hydroxide from group 1. So you'll see in the notes that those are the ones that are strong. Everybody else is weak because they're typically precipitates. As we go down to some math problems. Number 35 says, what is the most basic solution? So let's just pick one and then run with it. So we had these charts in our labs several times. So the pH here they give us hydroxide is 10 to the negative 14. So that's hydroxide ion concentration, that's 10 to the negative 14. This would be 10 to the 0 because these need to make 10 to the negative 14 as an exponent. Use these numbers, so that would be a 0, this would be a 14. So which one is most basic? If you have a hydroxide of 10 to the negative 14, you will have an H plus or hydronium concentration of a 0. So that's both of these. So those are the same basicity. And then here we have a pH of 0, that's the same basicity as well. So everybody's the same here based on our pH and chart, concentration chart. So remember, these need to add to 14, these need to multiply to that 1 times 10 to the negative 14, and they do. 36 says the strongest acid, we just need the largest number. The largest number is to the negative 4. Negative 5 is a 0 smaller. Here we have 4 zeros smaller and then 8 zeros smaller. So definitely much smaller there, much weaker. So if strongest is largest number, weakest should be smallest number. So find the smallest number, that's 10 to the minus 10, that's 9 zeros before that 4 and 2. So super small because it's super weak. Things that have larger numbers, here methylamine would have been the most basic because it would have the largest number. So look for that smallest for weakest and largest for strongest. In 38, they say, what are the ions in glucose? Well, that's a trick question because there isn't any ions in glucose. Anything that's organic, no ions unless you're an acid. And glucose is not an acid. So this is why the sugar in Gatorade is not very helpful. It gives you some energy, but it doesn't give you electrolytes. Sugars and alcohols in particular are terrible to drink because they're not going to produce any of those positive and negative ions that you're losing through your sweat. So no ions, and those are just molecules. This is what actually happens when you burn it. That's about it. So in 39 it says the acid. Acid is a proton donor in our newest definition with Bronsted and Lowry. So if we want a proton donor in 39, we need to give somebody, just like a kidney, we need to give them a hydrogen and pay attention who that is. Remember, the acids and bases are always reactants. The products are irrelevant, so don't worry about these as answers, so you can get rid of those immediately. It's these two that give and take the hydrogen ions. So HCO3 negative, so bicarbonate becomes H2. So it had one H, it now has two H's. So that must mean that it was a hydrogen acceptor, or a base. So notice it went from one hydrogen to two. That's what it means to be a base. Water had two, ended up with only one. That's because it gave its hydrogen to bicarbonate to make carbonic acid. So water here is an acid. Water can also be a base, but in this reaction, it donated one of its hydrogens, becoming hydroxide. Number 40 says HCl is a Bronsted-Lowry base because it increases the concentration of H3O+. Well, that's a little tricky because it is true that it increases the concentration of H3O+. That part's true. But it's not a base if you have the ability to increase H3O+. That means you're an acid. H3O+ is H plus acid plus water. And so that one's false because of the word base. Number 49 says hydrochloric, which is HCl, hypochlorous, which is HClO, and hydrobromic, HBr, produce only one H3O plus per molecule, and that's true because they only have one hydrogen each. They're all monoprotic. 54 says water can serve as Bronsted-Lowry acid and a base. So water is HOH. And if it's a Bronsted-Lowry acid, it's going to be a H plus donor. So if you get rid of an H plus, you're going to make hydroxide, and that's possible. So check, it can be a Bronsted-Lowry acid. And then to be a Bronsted-Lowry base, H3O plus could form because we could accept a hydrogen from somebody else and make H3O plus. So because it can accept, that's an H plus acceptor, and because it can donate, it can be both. So that is true. (57) says the pOH of a solution is 9. The H plus would be 10 to the negative 5, so let's make a chart. So pH, POH, H3O plus, and hydroxide. So they say the POH is 9, well then that would be 5 because these need to make 14. And if this is 5, this would be 10 to the negative 5 as an exponent, this would be 10 to the negative 9 as an exponent, and now that's true. Because of this 5 came from that 5. So 58 through 63, these are just examples of electrolytes. So non-electrolytes are usually organics. It could be gas molecules as well. And then electrolytes are things that were spectator ions from the previous chapter. They're typically ionics. So ionic salts, that kind of thing. So sucrose. Sucrose is a sugar. Sugars are organic, so definitely a non-electrolyte there. Hydrochloric acid is HCl. It separates into H plus and Cl negative 100% of the time because it is a strong electrolyte. Sulfuric acid even probably stronger. That's H2SO4. It can make 2 H pluses because it's diprotic plus sulfate. So definitely a strong electrolyte. That's how those batteries work. Gasoline is typically C8H18 plus other isomers, but in the end, organic. So it's hydrocarbons. Definitely not going to ionize. Be dangerous if they did. Cause rusting in your engine and other things like that. Sports drinks. Hopefully that's an obvious one. They're filled with K plus and Na plus and magnesium plus 2 kinds of ions. Those are the 3 most common electrolytes in sports drinks. And then seawater is definitely salt and water. So Na plus, Cl negative, and then water molecules. So definitely electrolytes there. More acid-base recognition. So the number of hydroniums is really just the number of H pluses. Hydrochloric is HCl. Chloride is a negative one. This is a positive one. So it's only going to have one. Nitric is H plus and NO3 negative together. It's only going to have one. Phosphoric acid is H plus and PO4 negative 3, so it's going to have 3. And then carbonic acid is H plus again, but now carbonate's negative 2, so there's only going to be 2 there. So you got to know your ions still, so keep your ion list handy, and these wouldn't be as bad as they could be. Here we have conjugate base, conjugate acid. So conjugate acid would be add H plus, conjugate base would be remove H plus. So here we have HCO3 negative. Well, it can't be anything with sulfur. To be a conjugate base, you have to get rid of H plus, and it has an H, so it couldn't have been this one either. So now we're down to, is it carbonate or hydrogen carbonate? Well, it's already hydrogen carbonate, so that wouldn't make sense at all. So it has to be the only one left. But remember, if your conjugate base is H2O3, that just means you remove H plus to get your conjugate base. You would add H plus to be a conjugate acid. So here we say the only one that with sulfur is sulfur. Could have been, obviously, does not have a conjugate base. That can happen too. So in this case, though, we're going to say A because it is the conjugate base of HSO3, because if you were to remove H plus, you get SO3 negative 2. It's also true, though, that it doesn't have a conjugate base, doesn't have hydrogen. So D could technically work in that situation, but A is what we want on our Scantron. Lastly, we have this table. If you did a little bit of the lab, you would have saw some of the answers. If you would have looked at the PowerPoint, you would have saw some of the answers. So here's those answers here from the PowerPoint notes. So So they're asking for milk of magnesia. So milk of magnesia down here. We have milk, which is up here. So 7 is neutral. Milk would be acidic. Milk of magnesia down here would have been basic. The other ones they're looking for is natural rainwater that has carbon dioxide dissolved. So it's going to be slightly acidic, just like soda. And then rainwater from industrial areas, that's going to even be more acidic. That's going to be the acid rain version of rainwater. So really in that situation, the only one that is basic is milk of magnesia. So only, so it loads up. Only milk of magnesia was basic. Everybody else, acidic, acidic, acidic. Of all three, this is the most acidic because it's going to have SO3s and NO2s that can make sulfuric acids and nitric acids. This one's just going to be carbonic acid based. And then milk has fatty acids from its lipids, making it slightly acidic. Even though this section wasn't asked about, it's a good review. Before we quit, just remember their definitions. For pH to be acidic, which would be B, you want less than 7. You also want H3O plus concentration to be greater or larger than 1 times 10 to the negative 7. So 1 times 10 to the negative 6 to the negative 5 to negative 4, all the way up to 1. You would want the POH to be more than 7. And you'd want the hydroxide ion concentration to be smaller than 1 times 10 to the negative 7. All these definitions work. Just think of the opposite definition for basic. So you'd have a pH for basic, you'd have a pH that's greater than 7. Hydronium less than 1 times 10 to the negative 7. POH less than 7. Hydroxide ion should be very concentrated, so it should be larger. So this could be the exact opposite for basic as you go through those. So now it's time to check them and submit them. And then now worry about week 12.